Let's look at the question, spiral matrix. We are given a matrix M multiply N. M represents the columns and N represents the rows, and we need to return all elements of the matrix in spiral order. Well, for some problems, the best way really is to come up with some algorithm for simulation. Basically, you need to simulate what programs ask us to do. We go boundary by boundary and move inwards. That's the essential operation. We go to the first row, the last column, then the last row, then first column, and then we move inwards by 1 unit, and then we repeat. So the second row now become our first row, and the second last column become our last column, and the second last row become our last row, and the second column become our first column. That's all. That's all the simulation we need. Think about it. When you want to switch the progress on one of the indexes, if you progress on I out of I and j, you'll be shifting in the same column. Similarly, by changing the values for j, you'll be shifting in the same row. Also, keep tracking of the end of boundary so that you can move inwards by 1 unit and then keep repeating. And remember, it's always best to run a simulation on edge cases, like a single columns or a single row, to see if anything breaks or not. The problem statement asks us to return all elements of the matrix in spiral order, which means we will start from the top left corner and move towards its right, and then down, and then left, and then up. Let's break this into further detail. We can achieve moving in different directions by modifying row and columns indexes. Specifically, we have given that we are at row and col, where row is the row index and col is the column index. When we move right, the col is +1. When we move downwards 1 unit, the row is +1. And when we move left 1 unit, and the col is -1. And when we move upwards, the row is decrement 1. So when shall we change our direction? We need to turn when either reach the matrix boundary or we reach the cells in the array that we visited before. Matrix boundaries are fixed and provided already, but how could we know if we have visited a particular cell or not? In fact, we have two different strategies here. The first approach, after we have traversed a row or a column, we can move the boundary toward the center of the matrix. Then, when we meet a boundary, we know it is time to change direction and update our boundary. And the second approach, while traversing a matrix, we can record each location that we have visited. Then, when we meet the matrix boundary or previous visited cell, then we know it is time to change our direction. The first approach is set up boundaries. Our goal is to update boundary as follows. When we finish traversing a row or a column, we want to set up boundary on it, so that next time when we get there, we know we need to change the direction. Here is a demo for the first round of the updating the top, right, bottom, and the left boundaries. The algorithm is like this. First, we initialize the top, right, bottom, and the left boundaries as up, right, down, and left. And then we initialize the output array result, and we traverse the element in the spiral order and add each element into the result. We traverse from the left boundary to right boundary, traverse from up boundary to down boundary, and before we traverse from right to left, we need to make sure that we are not on a row that has already been traversed. If we are not, then we can traverse from right to left. Similarly, before we traverse from top to bottom, we need to make sure that we are not on the column that already been traversed. Then we can traverse from down to up, but remember to move the boundaries by updating left, right, up, and down accordingly. And finally, we just return the result. Because m is the number of rows and n is how many columns in our matrix, so the time complexity is O of m multiply n. This is because we visit each element once, and the space complexity is just O of 1. This is because we don't use any other data structure. You remember that we don't include the output array in the space complexity. First, we have a C and R. C's represent how many columns we have, and I's represent how many rows we have. And then we initialize an empty array result to record every time we write down an element. And then we have a abscissa call, and it is overlapped with the upper boundary. Upper boundary is 0 now. And then we have a ordinate, it is row, and it is overlapped with the left boundary. The left boundary is 0 now. Let's build our right boundary. It is c minus 1. So how can we get that? Let's deduce. The upper left corner is 0, 0. The upper right corner is 0, c minus 1. And the lower right corner is r minus 1, c minus 1. And the lower left corner is r minus 1, 0. So the down boundary, it is r minus 1. So let's start our first loop. It is a loop from the upper left corner to the upper right corner. It is a for call in range left to right plus 1. And we can write down the element is 1, 2, 3, 4, 5. And then the next loop is from the upper plus 1 move to the down. So it is a for row in range up plus 1 and down plus 1. So let's write down the element is 10, 15, 20. The third loop is loop from right to left. So the result it is 19, 18, 17, and 16. And the fourth loop is loop from down minus 1 to the up. So we finish. This is our for loop to form a round. So after we finish this for loop, we need to increment the right boundary to move to the right 1 unit. Then we decrement our right boundary, so it will move to the left 1 unit. Then we increment our up boundary, so it will move to the down 1 unit. And then we decrement our down boundary, so it will move to the up 1 unit. So this is how this for loop works to form a round. Okay, let's implement the algorithm in the pattern. First, we need to initialize some variable like a result. It is an empty array, and we have already know the C and R represent the column. The R is row is the length of the whole matrix, and the C is column. We just find the length of the first row. And we have already defined the for boundary, the up boundary, the left boundary. They also start from 0, the uppermost, the leftmost, and they have a right. The right boundary, it is the rightmost, so it is c minus 1. And we have a down boundary, it is r minus 1, it is in the bottom. And then we have a while loop, while every time we write the result, so the result length, the whole length is less than r minus r multiplied c. In this case is 20, right? So we can add that much result. So every time when we finish result, we need to update our boundary, the up boundary, incrementer 1, move to down, the left boundary, increment 1, move to the right, the right boundary, decrement 1, move to the left, the down boundary, decrement 1, move to the up. And then before we increment and decrement and update our boundary, we need to traverse from left to right. So first we need to traverse. They have 4 traverse right in a round. First we traverse from left to right for call, because we only changed the call for in range. Start from left to right plus 1, and then we just append our result. To matrix up, because up is don't change. We only change the call, and then we traverse to the downwards for row in range. For row in range up plus 1 to down plus 1 to down, and then we append the result dot append and matrix at row, because we only change the row, and the right values don't change. And then we need to we have the third and the first And the fourth loop, we need to make sure that we are in different row. So if up is not equal to down, then we just traverse from right to left for call in range right -1 to left, and decrement by 1. So, and every time we finish, we'll just append the result. The matrix down, and the down is don't change, we only change the call. And then we have to make sure the fourth loop, we have to make sure we have in the different column. So if left is not equal to right, then we just traverse upward for row, because we only change the row in the range down -1 to the up -1 and decrement by 1. So every time we finished, we just append our result matrix, because we already changed the row, so the left on the column is don't change. And then after we finished, we can just return the result. Return the result. Yeah, it worked. The second approach, let's talk about mark visited element. If we mark the cells that we have visited, then when we run into a visited cell, then we know we need to turn. But how do we know which direction we need to turn to? Well, we are always following the loop to remember right, down, left, up again, right, down, left, up, right, down, left, up, and so on. Therefore, when we run into a cell that we have visited, we can simply turn to the next direction in the aforementioned loop. So the algorithm is work like that. First, we initialize a 2D array directions D to represent the 4 directions that we will move. Then we initialize the current direction, current D, to 0 to signify that we are going to move. We will move right at the beginning. But how could we mark the visited element? Note that elements in the matrix as row and call are constrained to greater than or equal to -100, less than or equal to +100. Therefore, we can select a number that is out of range and to mark it. Let's select 101 for marking purposes. But modifying the original data may not be a good choice sometimes. Therefore, we can also prepare another Boolean matrix to store the cells we have visited. So we just initialize visited to 101 to mark the visited cell. Then we initialize the change D for change direction to 0, initialize to 0, and we initialize row and call to 0. They represent the abscissa and ordinate. Since the initial position is 0, 0, then it is the origin of the coordinate. We just follow in the current direction until we reach the matrix boundaries or we meet a visited cell. While traversing in the current direction, remember to reset change direction to 0 after every step, and we have to move to the next cell by updating the row and column indices, and we append the element to the result and mark the location as visited, and then we update the direction and update the change direction. But the last puzzle piece is, when shall we stop? An interesting observation is that if we reach a visited cell, we need to turn. However, when we meet another visited cell immediately after changing the direction, it means we reach the last element in this matrix. You will see that it is an integer change direction, change D. It is used to track the number of times we have changed direction consecutively. So if change direction is 2, which is larger than 1, it means we are continuously changing our direction, and therefore we are already visited all of the elements. Then we have to finish. Let's analyze its complexity. Because we visited each element once, so the time complexity is O of m multiplied n. M is the number of rows, and n is the number of columns, and the space complexity is just O of 1. This is because we don't use any other data structure. Remember, when we calculating the space complexity, we don't consider the output array or the input matrix. They don't use any space resources. However, if we were prohibited from mutating the input matrix, then this would be an O of n multiply n space solution. This is because we would need to use a Boolean matrix to track all the previously seen cells. Okay, let's implement the algorithm in Python. First, we need to define our visited is 101 because we need to pick a number that is bigger than the 100. 100 is our restriction, right? And then we need to initialize R and C. They represent the length of the matrix and the length of the first row, and we initialize the for direction, D for the direction, and they have a for state. 0, 1 means move to the right 1 unit. 1, 0 means move downwards 1 unit, and 0, -1 is move from right to left 1 unit, and -1, 0 move from bottom to upwards. So after we have this four states, we need to set a pointer to track in the D. So current D direction is to it first start from 0, which means that the first 0 means the first state is move to the right, and we need to set a variable change direction. Is also start from 0. This is how many times we change our direction. So, and another variable we need to declare is row and call. Row and call is both of them is start from 0 because it work like bit like opposite and ordinate. We start at the beginning 0. So this variable row and call will keep tracking where in which location we are going to. It is like the opposite and the ordinate to track our elements in the 2D array. And so row is represents the row, and the call is represent the column index. Both of them is the index in the 2D array. And then we need to set a result. Result is because it list have one element. The result is an array. They have one element it will store the first element we made matrix at 0, 0. Means this is origin point, and because we already record the result, record the matrix 0, 0 in our result, so we can modify it to the visited. So the 0, 0 now is modified to visited, and then this is how we declare the variable. After we declare a variable, we have a outsider while loop. The most important is a change is control when we stop. So when the change direction is less than 2, it will continue. So where it is true, when it is less than 2, that means only 0 or 1. So 0 means keep go on, and 1 means we need to change. So because the change direction will increment and change, and then we need to use another variable next underscore r. It will automatically add it depends the current direction at D at 0. So this time that means we use the 0 state, the first state of the D. It will move from left to right. That means the next row will move to the right 1 unit, and the next C is called plus D, and at current direction at 1. That means the second state, which means they will move from top to bottom, move downwards, and so it will be add to 1. So this is the next R and next C. We can directly use the next one, but we need to judgment whether we can use. If it is meet our demand, we can use it. And another is we need to make sure when we stop to make sure it in the boundary. So if it is not in the boundary, we just stop. If it is the next 0 should bigger than 0, and the next R is always less than R, because R is our max number is how many value it can hold, and also the next C is also less than C. So if it is in this, that means we are in the boundary. If it is not, it will run out of the boundary. If it is out of the boundary, then we need to break. And another is if we meet the element we meet before, like it is a visited cell, we also need to break if matrix at next at R and next at C is visited. That means we meet before. If we meet before, we just break the loop. And so after do that, everything is after do that, we need to reset the change. We set the change D to 0. So every time we use it, we will change it to 0. We reset it to 0 since it already breaked, and we can change. So that we can change the direction, and then we can update the current position to the next step. Because if the value is passed here, that means it is meet our requirement. That means it can directly use. So we just get the value from there, and then we just add the result, append matrix at a row at core, and then we just we append them to the result, and then because we add them to record it, so then we can mark it as, because we just use it, so we can mark it as visited, and then we can change our direction. So every time the current at D is every time we change it will it will increment by 1. But if it is meet 4, until it's 4, if it is 4, it will become 0, like 0, 1, 2, 3. So 4 is come here, come the first one. So every time it's multiplied by 2, every time it's come to 4, it will automatically become 0. And finally we need to increment the change direction, because we change the direction. The change D is increment by 1, and then we can return the result. Oh, matrix. Yeah, that is how it works. 1, 2, 3, 4, 5, 10, yeah, and